So, hello everybody. Thanks for being here this late hour. I realize that I'm in the way of your way home to your families or the near loved ones you have. So I'm trying to keep this a bit short. My name is Per. I'm the CTO of Speedment. So I'll see if we can make this work. Next. Well. Okay. So I have the laser. That's something. Okay, yeah. So this is a little bit about myself. Can anybody see where this is? You don't have to guess. But yeah, good guess. It's not Stockholm, it's Gothenburg. So that's where I'm from. And it's dark, so presumably it's in the winter times, because it's always dark in the winter times there. It's so up north. Started with computer when I was 14, built this kit, because I couldn't afford anything else. Started with Java when Java came in the middle of the 90s. This is my third startup I have. Moved to Silicon Valley half a year ago, and I love it here. Obviously, the weather is better. I have a Java blog that I run with about 500,000 reads, so it's becoming very popular lately. So that's cool. So this is a scenario I'm going to talk about. Here we have a lot of databases, one or several, and they are the source of truth. So potentially you have a lot of application making updates here. You can have scripts, or you can have old application, backend, whatever, pushing in data here, and you have a lot of data. I said more than 1 terabyte, but think like 2 terabytes or 10 terabytes or whatever. There's a lot of data. And then you have an application, and you want something in between, and maybe you have a web shop or a stock trade or bank or machine learning or whatever in between. So the question is, how do you do this? How do you put in something in memory there in between so it's consistent and efficient? And what kind of trade-offs are there? So that's what I'm going to talk about. So the scenario is we have a lot of data, we have existing databases, and we want to make that available in a good way to our applications. And of course, there are some pros of this. Of course, you get improved performance. That's important. But what might be even more important is that you have consistent performance, meaning that you can kind of promise that I get some kind of performance. If you have a database, often you're lucky, you get a response in maybe 100 milliseconds or so, but sometimes you're not that lucky. You wait 1 second, maybe 10 or 1 minute for your data, and that can be devastating for your application. So we get more consistent operation. We also can get cost reduction, because potentially we're executing much more efficiently. We can have smaller servers, we can reduce the number of nodes we have in AWS, or we can maybe reduce our database licenses. But there are also some challenges. How do we get the optimum speed? What about costs? We said we have terabytes in the memory. How can you get that? Isn't that very expensive? And are there so big memories available today? What about consistency? How do I ensure that the data I have is really reflected in a consistent way in my cache? How do I restart? What's the impact of the database, etc.? And if we solve all that, how am I going to organize my JVMs? Do I want one big JVM, or want 10,000 small JVMs, or something in between? What are the parameters? So these are the things I'm going to talk about. I'm going to start with speed. And I kind of postulate something here. It doesn't matter how advanced or quick database you may ever have. All that matters is the locality of the data. You want to have the data you're working with as close as possible to your application. That's key, and I'm going to describe why. And another thesis I have is eventually memory will cost less than X dollars per gigabyte. Pick any X. So it doesn't matter what kind of figure you come up with. It will be, in a relatively short period, cheaper than that. So I'm going to talk about us humans. We are good at medium kind of things. We know that an apple is kind of smaller than a football, but it's very difficult for us to relate the distance from one star to another star, or the distance between one atom to another atom. We live in the middle world. We don't understand that so easily. So I'm going to use an analogy with time here. So instead of talking about nanoseconds or microseconds or seconds, I'm going to talk about the distance that the light will travel in that distance, because that's more scales to something we're used to. We don't know how much a nanosecond is, but we know what a foot is or something like that. So as a reference, I'm going to use a database query that takes 1 second. Now, arguably, a database query might take much less than 1 second, but it also might take much longer. So this is just a reference. Does anybody know how long time it will take, how long light will travel in 1 second? Any suggestions? Yeah? Yeah, exactly the right correction, but is there a correlation to something we can understand? It's obviously 3 to the power of 8 meters, but that's exactly what I wanted to see. It turns out it takes about 1.2 seconds for a light to travel from the surface of the Earth to the moon. So that gives you a kind of scale of this. Now, if we look at other typical events within the computer area, like a disk seek, now we heard about that we should not use magnetic disk, but if we have a magnetic disk, it will correspond to the light traveling from here, from San Francisco. I will go get my laser beam while it's here. So I can go here, where we are right now, in San Francisco, and the light will travel all the way down to Los Angeles, maybe down here to Disneyland or something, I don't know. So that's a disk seek, and if you send a TCP package, that's a bit shorter, from San Francisco here to San Jose here. That's much closer. And if you're going to pull in a block from an SSD device, it's from here to Oakland, just across the pond here. So that's certainly much closer. So now we're getting somewhere. Now I'm going to talk about memory. So memory is quick. So you might recognize this venue here. It's the very room we're sitting in. And before my presentation, I did some pre-measurement. So if I start with this line, and I go in this speed. Now I go with 1 million the times of speed. So the speed is 1 million times quicker than I'm right now. I turn around here, and I go back. And if this is 1 million times slower, then this is 100 nanoseconds. So this corresponds to 100 nanoseconds. When I went from this line to the line over there and back again. So that's much shorter than going to the other side on the pond, for example. If I'm lucky and get to the L3 cache, it's like going from like this gentleman here to this gentleman here. That's much closer. So it's even faster. So if we go to level 2, that's about 20 centimeters or 8 inches. So if I relate that to when I was walking, it's like from this to this snap, this time period. And if it's an L1 cache, it's just 4 inches, so 10 centimeters. It's like this. So if you compare this to walking to the moon, you understand the magnitude of the difference. This and walking to the moon. It's a great difference. So that's my point. It's a huge difference of having it remote on the database or having it near close to your application. OK, so what about cost? I will use another analogy. This is Back to the Future, a well-known film. And we ask ourselves, how much does a gigabyte cost? Well, of course, that depends on when you ask the question, obviously. So if we look at recently, maybe 6 months ago, 1 gig will set you back like $5. Doesn't sound so much. But if you go back to the start of the era of the computer era, it's much cheaper, much more expensive, of course. So it's about this, $6.7 billion. And of course, you couldn't buy that amount of memory because there weren't so much memory in the entire world at that time. But if it would cost something like that if you just scale it up proportionally. And somewhere in between, incidentally, when this film debuted at 85, it was much more expensive, but still much more cheaper, but much more expensive as today. So it's about $1 million. So what about the future? Well, no one knows, but I wouldn't be surprised if we would pay like 4 cents or something for a gig in 15 years. Perhaps less, because there might be no advancement in the technology area. Maybe we have graphene kind of memory or or a DNA memory, or I don't know. We don't know. No one knows. So, but you can also turn the question around and ask yourself, how much can I get for a cup of coffee? And we are reaching a turning point right now. For the first time in the history of mankind, 1 gigabyte will cost less than a cup of coffee at Starbucks. So this is really a milestone. So you can see right now, it will cost you 1 coffee at Starbucks. And in a few years, yeah, it's much less. So you get the analogy. It's cheap and getting cheaper. Okay, so look at the consistency. And this chapter is going to be a little bit more cognitively challenging. But there are different ways of keeping your cache up to date. A very simple method and good method is to use something called dump and load. You have a database, you reload everything in your memory, and data remains unchanged between reload. Typically, you do this at 9 a.m. in the night. So you load everything you have, you structure it, and then you have it the entire day. And then the next day, you reload it again, start all over. And if you have to restart the system, you just reload. Then you're back again. And there are a collection of other methods that I collectively called POL, which is kind of, you have something, you evict it, or you refresh it, or you mark it as old. So you have a certain time to live, or TTL, as we nerds say. And the evicted elements are reloaded from the database. So when they expire, you have to reload them. And then, of course, data changed all the time because you expire stuff and you pull them in from the database again. And if you restart your system, you have to warm up, or you can start with the cold cache, but then, of course, your performance will not be that good. Then we have something I'm going to talk a little bit more about called the reactive persistent caching. In this scheme, you really capture what's changed in the database, and you push that into the cache as it's happening. And you group the event into the transactions. So you have a transaction with several updates, you group them together. And you also persist your cache here. So everything that updates the cache is also persisted locally at your node. And in this case, of course, data changes all the time. And if you restart, you only have to replay the missed events. So you can start off from where you crashed, or where you restarted, or where you brought the node down from maintenance, or whatever. So this is a comparison between the methods. If you have dump and load, your max data age will be typically the dump period, say a day or so. So your data is 1 day old. With the eviction, it's the TTL eviction time, which is usually like 2 minutes. So you evict data after 2 minutes, and if you're unlucky, your data is 2 minutes old. That's trivial. But in the reactive persistence caching, you feed data in all the time, so then your data is only like milliseconds old, like 10 milliseconds or 100 milliseconds. So you have a much fresher data set. If you look at the lookup performance of your application, you're consistently instant with the dump and load because you have everything in your cache and you can use it instantly. You don't replace it. So it's always there. But if you look at the POL caching, with perhaps 20%, it depends on how you use the cache, but might be 20% of the times you will miss the cache and you have to reload it. And what do we do when we have to reload? What do we do then? I will launch a space mission. We are going to the database. So everything is going to be slow. For 20% of the times, we're going to be extremely slow. So here it's a very poor method. Reactive persistent caching is good because everything is there. It's updated in background all the time. Looking at consistency, of course, this is if you stretch the meaning of eventually consistent, you can argue that the dump and load cache is eventually consistent. That means that it reflects a valid state of the database in the previous time. You don't know how far back in time, but now it's 1 day. So it's eventually consistent, but not really what we mean with eventually consistent, because usually we think in seconds, but it is eventually consistent. Looking at the POL caching, it's inconsistent, and it's worse than that because it's inconsistent between tables, and it's also inconsistent within tables because you don't have a clue when things are updated. They're just updated randomly when they expire. So one is expiring this time, another one, and you might have done several updates between when you read this cache entry and the other cache entry. So here we have a completely inconsistent view of your data. If you look at the reactive persistent caching, it's also eventually consistent because you update all the events that are grouped together in a transaction atomically in the cache. So it's eventually consistent, and the delay is much, as I said, it's in the region of milliseconds. So this is more true, eventually consistent. Now, if you take the other view, if we now are thinking that we are the database, what loads are imposed on the database? What penalties do we have? Well, of course, for the dump and load, the database load is proportional to the size, because we load everything each day. So if it's 100 gigabytes, we load 100 gigabytes per day. If it's 200 gigabytes, we load 200 gigabytes per day. It's simple. The poll caching, this is really when this sucks. Everything here is evicted, so we might evict stuff here 1,000 or 10,000 times, but it's never changed. So we might reload stuff maybe 10,000 times, and it's never changed. So you're imposing a tremendous load on your database. So if you use your entire cache and the entire set of data here, you will reload it maybe 100 or 1,000 times per day. So this is really a disaster. If we look at the reactive persistent caching, it's only proportional to the rate of change. That's a big difference with the two others. So if I don't do any change, the load is 0. If I do like 10 transactions per second, the load is 10 transactions per second that I get into my cache. And looking at restart, if you restart the dump and load, you have to reload everything from memory. And I said before that we might have like 3 terabytes or 10 terabytes. Does anybody know how long time it will take to load 3 terabytes from a disk or from a database if you have a fairly rapid sub-disk system? 3 terabytes. 3 days. Not so good if you have a mission-critical thing. So I guess that's the drawback with this for really large data sets. You need something that can produce a high data rate. Okay, poll caching, it depends on the eviction time. So, I mean, if you let it run on the side without using it, it will successfully build up your entropy in your cache, so it will become better, and then you can switch it in. But an interesting feature with this reactive persistent caching is that it's only proportional to the time you were down and the rate of change. And usually that's about 10%. So if you're down 10 minutes, it will take 1 minute to fast forward to where you are. And if you're down 1 minute, it's like 5 or 6 seconds. So, you know, I think you got it, but I've kind of highlighted the good properties here. So I think certainly this scheme is something to consider out here. Okay, so how do you organize your JVM? And now I'm going to be a little bit more, even more technical. I'm going to talk about object pointers and registers, stuff like that. So yeah, if you don't like that, you might relax for a while and you can come back on the next issue. There are basically 2 ways of doing this. You can scale up, and scale up means that you put all your data in one node and make it bigger and bigger as data grows. And the other one is scale out, so you have several nodes. As data grows, you just add nodes. So one JVM handles all data in a scale-up solution. Usually you don't have that much RAM, so you can map your data or your JVM memory to SSD-backed files. So you can have the JVM can be substantially bigger than your RAM. And a good thing when you do this is that several JVMs can share the data, so you can spin up several JVMs sharing the same files, thus sharing the same maps. And it's instant restart. So you spin up a new JVM, and it will share by the file system. It will get its content directly. Scale-out solution, you have several JVMs in the network. You typically sharding between nodes. So you have like names that begins with A on one node, names that begins with B on another node, and so on. And often you have redundant nodes. So if one node goes down, then there's another one taking over. So you have a duplication of your data sets. So before we go further, we need to understand how a Java program works normally. Normally, you have data objects living on the heap, and they're garbage collected. You create something, and then you just forget about it. You don't have to free it explicitly. That's something the system does for you, but at a cost. And the problem is that the larger the heap size is, the larger it takes to collect garbage. It's like if you have a long street, the garbage man takes longer to drive, of course. And the other thing is that the more you mutate your heap, that is, the more you change your heap, the more the garbage collector had to consider. That corresponds to the more garbage bins you have, the longer it takes for the garbage man to pick it up. And they work together in a vicious circle. So the bigger Java heap you have, the more likely it is that you mutate it. So it's a bad thing. And the term by Java expert is that the app has hit the geeky wall. It doesn't matter how much processing you put in there, it doesn't matter what you do, you can't make it bigger. And that is somewhere between 10 and 20 gigabytes, maybe 16-ish kind of JVMs you can have. Otherwise, you will have GCs that are very long. So if you have 10 terabytes of data and maybe you decide for 10 gigs, you will have 1,000 JVMs. And you can have 1,000 JVMs, but certainly from a practical point of view, it's not desirable. So you need to come up with something else, and that's why you have off-heap storage. And off-heap storage is that you have a Java object, you serialize it to byte form, and you put it there, and when you need it, you read it back. So the garbage collector will not see it. Maybe it relates to if you have garbage and put it under the mat, so the garbage collector doesn't see it. And you can scale up to terabytes in main memory, and you can map this memory space to files. So now we can use any nodes for our scale-out solution. We can have 2 nodes, or it doesn't matter if we have off-heap storage. So we're free again to choose how many JVMs we need. But then it's about persistence and reloading. So if I just have one node, like here, there is a certain bandwidth limit that I can read my data. And usually if you have SSD, it's about 1.3 gigabytes per second. So if I can reload 1.3 gigabytes per second, take me 6 seconds to start up 10 gig, 1 minute 100 gig, and 10 minutes 1 terabyte of data. And 10 minutes is kind of long. You don't want your application to sit idle 10 minutes. So what you can do is you can build a system with several nodes, like 10 nodes. So if you have 10 nodes, you have 1 active and 1 backup, so that means 5 times more power. So then it's 5 times quicker. So then you can read 1 terabyte in 2 minutes. That's certainly much better. And you can have, if you have 100 nodes, it just takes 12 seconds to load 1 terabyte. So this is a factor too you have to think about. So now we're back again with a lot of nodes. So this is really a trade-off you have to do. And there is another factor here, and that is that you can have different pointers in Java. In Java 7, you can have something called compressed OOPs, which means that you can use a 32-bit addressing, but you can shift it 3 steps. So you get 8 times bigger memory. Of course, you have to align your objects on that boundary then. And in the event of Java 8, you can align it in 16 bytes. So you can double your memory. So you can have 64 gigabytes of memory, but only using 32-bit references. And why is it important to have 32-bit references? Why is that better than 64? Anyone? Why would I rather have 32-bit references? Because they're smaller, obviously. So I will use my cache much more efficiently. My memory will become much more compact. So once I switch over the 64K, I will pay a penalty. So an equivalent to have 64K, I will have to go up to maybe 80 gigs to get the semi-effective storage. And my performance will be less because my caches will not be so efficient. So there's kind of sweet spot here. So if you pick the size of 50 gigabytes and you use off-heap, then that's a kind of good thing, I think. Then you have 20 nodes per terabyte, or 40 nodes if you have a minimum of redundancy. And I think that's reasonable. I think that's a reasonable size, gives you a reasonable amount of JVMs, and gives you the best performance. OK, so conclusions here. Get speed by keeping your data close to the application. RAM is cheaper and getting even cheaper. You can have a consistent solution with reactive persistent caching. And it's also a minimum load on the database. You can scale up your solution either vertically, by using memory mapping and maybe virtual memories that we heard about in this in the talks before here. And you can scale out solution using kind of 50 gigabyte nodes. So what do I do then? We have a tool here that can fix a lot of things around this thing. We have the data here, and you have your application here. And what we have is a Java development tool that has an in-memory JVM cache with very low latency. It's a scale-up solution. We have something called a SQL Reflector. Let's see now, that's a laser. That capture data in the database, and it can propagate that change to our own, but we can also use Chronicle Map, Hazelcast, or GridGain, or whatever that's out there, so it's kind of vendor agnostic. There's a code generation tool, so it can derive the entire domain model from the existing database. So we just connect them to the database, and you get all the code generated, and you can start using it directly. And it's a transaction aware. So the scale-up solution is ultra-low latency, and we're talking about nanoseconds, maybe 200 or microsecond, 1 microsecond or so. You can have latencies, measured in microseconds, I would say. And millions of transactions, and it supports file mapping, terabytes of data, and it's order 1 for equality operations and order log n for other operation. This is kind of a geeky, denotion, but it says that the bigger the cache gets here, it doesn't matter how big the cache is, you will find equality operation in constant time. So if we have 1 terabyte or 100 terabyte, doesn't matter. I will find what I'm looking for equality in constant time. This means that the bigger my cache is, it will take a little bit longer time, but not that long, if I translate this to English. So what about the reflector then? We detect changes in the database, we buffer those changes, and we can replay the changes later on. We'll preserve the order which they were made, which is important, of course. We preserve transactions, and we will see data as it's persisted, because maybe you have triggers or stored procedure or anything that modifies the data. So we will see what's actually put in the database. And it detects changes from any source. So it doesn't matter how you update your database. It can be your own application. It can be a third-party application, scripts or stored procedure or triggers or whatever. It doesn't matter. We will sniff it up. And so you can feed it to, for example, Hazelcast in this example here. You can download this. There's a free trial. Go to our homepage. And what you do is you connect to a database, select the type, IP address, and schema you want. It derives the schema from it automatically. You push that button over there, and you get a lot of code, and then you're up and running. You can use it immediately. So it's very simple. So this is what we offer, a complete solution for in-memory hot big data. We license our products, and we also help you make your dreams real, to get your data instantly. So thanks for your time, and thanks for staying so late. Thanks. So do you have any questions? So I'll be happy to answer, yeah?
How do you detect all these changes in all the different kinds of databases?
Question is, do we detect all these changes in all types of databases? Not all of them, but certainly most of the most commonly used, like Oracle, MySQL, Postgres, DB2, yeah. Some are the greater, but there are some we don't cover, but they are very seldom used. So if you have a specific, something you want to do, you can just talk to me, and we can see if we can fix that. We're not relying on any secret things. It's just SQL, standard SQL.
Then you have to do continuous following?
No, it's built on triggers. So you have triggers in the database, and you harvest that. So that's how this works. Yeah. More questions, please? Thanks. Thank you.